Hello everyone, welcome back to the video lectures on image and speech processing. In the previous videos we have been talking about the image compression models. So in today's class we will be talking about one of the image compression model, right? So in today's class we will be talking about our block transform. Then how is this block transform related to JPEG and JPEG 2000? Right, we all know that JPEG and JPEG 2000 are the file extensions of our image, right? So when you save an image, JPEG, PNG, BMP, right? All these are basically the compression models or the compression techniques that we are using for image compression. So those extensions are obtained from the compression models, right? So we'll be talking about the block transform and JPEG, then a slight discussion on the JPEG 2000, right? So let's go into it. So block transform basically is of this block diagram. So how is this block diagram is, we have an input image of size m cross n. From this m cross m, we will construct an n cross n sub image, right? So basically we divide an image into small and that too non-overlapping blocks and of equal size. What is the equal size of that? Small n cross n, right? And we process the blocks independently. So we will divide the image into sub-blocks, and each sub-block is considered as a single unit of or single image. So that image we are going for the processing, right? Then we will perform the forward transform. So what is that forward transforms are? Those are the image transforms which we have dealt, right? So what are the image transforms? We have read about DCT. We talked about DCT, DFT, discrete Fourier transform. This is discrete Fourier transform. This is discrete cosine transform. Then we talked about Walsh-Hadamard, and we even talked about HARP. So there are two others, which is called as the slant KL transforms, which we have not dealt with, but these are the important image transformations that we have talked about, right? DCT, DFT, Walsh-Hadamard, HAR, slant and KL, right? So each whatever sub-image we are considered, that we are independently considering them and performing the 2D transforms, right? So each sub-image is mapped into a set of transform coefficients, right? After that, we will this transform coefficients, whatever we have got, that we are doing the quantized. So that we are passing it through the quantizer. So the quantization process is done. After that, we are passing it through the symbol encoder. So what does the symbol encoder does is, it is either half-man coding or run length coding, which will decrease your run length, right? So while doing all this, what do we consider here is the small magnitude coefficients can be coarsely quantized with little image distortion. Okay, so if the magnitude of the coefficients it is very small, then we can neglect it. If it is very small, then we can neglect it. If it is a small quantity, then we are coarsely quantizing it. So using this process, we are able to achieve our image compression. So if you observe here, the quantization is the process where image compression is achieved, not at the transform process. So after the transform coefficients, at the stage of the quantizer, we are able to get our image compression, right? So let's go into in detail here. So let me just go back here to the block diagram here. So if we consider that each block is important for us when we are going for the compressed image. So what should be the size of the sub image? What kind of a transformation should be selected, and what is the quantizer that we have to select, and symbol encoder? All this play an important role while going for the compressed image to achieve a compressed image. So this compressed image can pass through a simple decoder because we are going a simple encoder. So symbol decoder is required. Then a forward transform is done. So the inverse Fourier inverse transform, whether it is an inverse Fourier transform, inverse DCT, or inverse Walsh-Hadamard, or inverse Haar, right? So after that, we are going to submerge all the whatever split we have done in the first stage of here, that we are going to merge all the sub images, then to achieve the decompressed image, right? So we will be talking about each of the block which is required, how do we select it in detail, right? So the first what we are going to talk about is the transform selection. How is the transformation technique that is selected? So the particular transform that we are choosing is application dependent. Okay, it is application dependent, and it is also dependent upon the how much construction error or reconstruction error, as well as the computational resources that are available. What is the reconstruction error means? The decompressed image whatever we have achieved, that should be very similar to your original image. There might be a small error, but the error, how much error is accepted, and that's for specific application. Based on that, we will select our transform. Whereas the next computational resources, what do you mean by computational resources is, do we have a fast computing software or fast computing CPU? So based on those computational sources, we will decide the choice of our transform. So as I said before, compression is achieved during the quantization of the transformed coefficients, but not at the transformation step. This is a very important point, because most of us think that when we are transforming, we might be achieving a compression, but no, actually no. So this quantization is achieved, the compression is achieved at the quantization level, right? So if is a transformation function, if we are representing is this in way, then our the image or the whatever f of x comma y, which is in spatial domain, okay, after doing transformation, we can represent our image as in this form, where t of u comma v is the transformation function, and suv can also be written as our input image, right? So this is the equation which represents the output transformed image, right? Now we define a transform coefficient masking function. This is another important parameter. Okay, why we have to go for this masking function is, we, as I said before, the small coefficient or the small magnitude coefficients are costly for quantized, or they are neglected. So which are the transform coefficients which are like small in magnitude should be decided. So that is defined by your masking function. So what do we do is, we define the masking function as eta or gamma, where it is 0 or 1. When it is 0, if TUV satisfies specified truncation criteria. 1 otherwise, right? So this is the masking function that we follow, right? So when eta of this is defined to eliminate the basis image that make the smallest contribution. So that is when we're reconstructing the image, the small magnitude contribution of the coefficients can be neglected. They can be assumed to be the previous one or the next pixel value. So these coefficient values can be neglected. So using that concept, we are going to differentiate, or we are going to define this masking function. Masking function is defined in such a way that it is 1 for if the thresholding or the threshold criteria is not satisfied. If the threshold condition is satisfied, it is made as 0. So when we are neglecting the small magnitude coefficients and trying to reconstruct that is represented by g cap of u comma v, right? If I go back, we just go back. So this is the image function or the image reconstructed when we are considering all the transformations or all the transformation coefficients. So this is considered, this equation G cap we are considering when we are neglecting our the small magnitude coefficient. So that equation is given by this equation G cap of u comma v is equal to double summation of eta of u comma v, t of u comma v, su. So this is the masking function, and this is the transform coefficient, and this is our input image, right? So we have various transformation techniques. So among them, which is the best means, we have KL transform, which provides the minimum mean square error. Okay, so mean square error between the transformed image and the mask transform image. So when I compare this G cap as well as my G function, KL transform, even after putting my masking function also, I get the minimum mean square error. So why not go for all this is, we don't use KL transforms very often because it is difficult to implement, because it is very computationally difficult to calculate and all. So even though we have a minimum mean square error, we don't go for the KL transforms. But whereas we have the other transforms which are non-sinusoidal transforms, they are very easy to implement. And we also have the sinusoidal transforms. They are easy to implement, and we can combine lot of our data to combine, and more packing of the data is possible. Whereas this packing of the data is very it's not possible. I cannot say that it is not possible, but we can say that the packing of the data is not that easy. So for that, if we have KL transforms, non-sinusoidal and sinusoidal transforms, sinusoidal transforms are the best because they are easy to implement and more packing of the data. And it is very similar to our KL transforms. So the drawback of a KL transform, which is like difficult to implement, it has been removed here. So we go for sinusoidal transforms. In sinusoidal transforms, if we take our DCT transform technique, okay, what are its advantages are, it is implemented in a single integrated circuit. It can be implemented using a single integrated circuit, and packing most information into a few. So using a few coefficient values, we can combine lot of the data. So image compression can also be achieved using this, right? So next, we are decreasing the blocking artifact. Okay, we are trying to decrease our blocking artifact. So based on these three advantages, DCT is mostly used in our transformations. Okay, next important parameter in our block transform is the sub-image size selection. So sub-images size are, it's a very important. So images are subdivided so that the correlation between the sub-images is detected to an acceptable level. So when we divide it into subgroups, the relation between one subimage to another subimage, that correlation or the redundancy, should be reduced to a level which is acceptable. Okay, this acceptable level is different from one application to another. So based on our application, we can divide into the sub images, right? The size is dependent upon that. Based on that, the most popular sub-image sizes are 8 into 8 and 16 into 8. So we will see later in our video that 8 cross 8 is used in JPEG. Okay, in JPEG we are using 8 cross 8 sub-images sizes, right? Next is the bit allocation. So how is the bits allocation done? So in the reconstruction error is the function of the number of and relative importance of the transform coefficients, the precision of the retained coefficients. So is the reconstruction error is a function of number and relative importance of the transform coefficients. That is, how many coefficients are being generated, and as well as the masking, and how precisely the coefficients that are retained are helping in our reconstruction. So all these parameters help in our bit location. So the retained coefficients are selected based on zonal coding and thresholding. So How are the retained coefficients done? They are done by masking. So what is the masking? How is the masking done? Is dependent upon either it is a zonal coding or thresholding. Okay, the overall process of truncating, quantizing and coding the coefficients of a transformed subimage is called as the bit allocation. So basically whatever subimage we have done, based on that we are doing our transformations. The transformations, after the transformation we are doing the truncation, we are selecting the or we are neglecting the small magnitude coefficient. So that part, how we are doing our quantization and how the coefficients of the transformed subimages are coded, all these three things are combinedly called as the bit allocation. So we will see what is zonal coding and how is it used for masking, right? The transform coefficients of maximum variance carry most of the image information, right? So in zonal coding we are assuming that the transform coefficients which are having the maximum variance will have the most of the information, so those should be retained, right? They should be retained in our coding process. The others which are having the lesser variance can be neglected. Okay, using this method, the zonal marks is created by placing 1 in locations of the maximum variance and 0 in locations of the other locations. Say suppose we have an intensity value that we have transformed into Fourier using a DCT, and we have got the coefficients. So those coefficient values we will check its variance. Specifically for one coefficient value we will take and we will try to calculate its variance. If that variance is of maximum value, we will put the place as 1. And for other locations, we will put the value as 0. Right? So the coefficients of the maximum variance are located around the image transforms. So this is usually assumed. This is an assumption, and it is reality check is also done by taking different examples, and we observed that the maximum variance coefficients, the coefficients which are having the maximum variance, are in and around the origin of the image transformed image technique. So let me just erase this for a minute. So usually we know that the origin of the image is always at the left side corner, right? So if this is our origin of my image, then I observe that this I have my maximum variance. So I have a maximum variance means I will put my mask as zonal coding as 111, right? So in and around my origin I have my maximum variance which is represented by 1. The other all are represented by 0, right? So based on this, when we are doing the quantization, we are going here by representing it by 8, 7, 6, 4, so on, the number of bits. So this 8, 7, 6 define the number of bits that are used to represent in the quantization. Right? So next, the coding technique, the next masking technique is the threshold coding. So in threshold coding, how is it different from zonal coding? Is zonal coding is implemented using a single fixed mask, right? And that way it is used for all subimages. Irrespective of how the variance is done, the same mask is used for all the subimages. But whereas the threshold coding is adaptive in this sense, it is the location of the transform coefficients retained for each subimage vary from one subimage to another. Because the location of the transform coefficients retained for each subimage vary from one subimage to another, we will use an adaptive. So thresholding is one such technique where an adaptive mask is generated based on the location of my transform coefficients. So this is much more advantageous than my zonal coding, right? How is this here masking done is the locations of the maximum coefficients which are represented by are reordered to form the one length coding. So basically whatever we have the locations, the maximum coefficient values, they are reordered to form the 1D run length coding sequence. So using this one length coding sequence, this is passed through a symbol coder. symbol coder, and we are going for the coding technique. This is computationally simple. When we compare the zonal coding as well as threshold coding, it is adaptive in nature, and as well as it is computationally simple for implementation. There are three types of threshold how we can implement it, right? So we have a single threshold, adaptive threshold, and it is a function of location of each coefficient in the subimage. One such example is here, right? So the coefficient values which are having the maximum variance or here are represented by 1, or maximum which are adaptive, or maximum which help in reconstruction of the image are given 1, rest all are given as 0. So this is a threshold mask, right? Now, using all this information, we will try to understand the JPEG, how a JPEG is implemented for an image, right? So, if I say a image, say p1.jpg, a JPEG is an extension of the image, but it is not a file format like how we have like PDF dot PDF or dot txt. It is not an extension of the file, but it is actually shows what type of image compression technique that is used. So JPEG is one such technique which uses block transform, right? So therefore, image compression uses block transform coding technique. It uses the block transform coding technique, and the sub image size is 8x8, and the transform technique that is used is DCT, and these DCT coefficients are quantized according to psychovisually tuned tables. So this is an important parameter when we are going for a JPEG coding technique. So this quantization is done using a psychovisually tuned tables. We consider those tables and we will try to quantize these DCT coefficients. These symbol encoded or this psychically tuned tables or quantized output will be compressed using the run length coding and half length coding, right? Now, we will go step by step how this JPEG coding or JPEG compression is achieved. So the first step what we have, say suppose we have a whole image of 512 cross 512. So what do we do is, first step we will divide the image into sub images. Okay, sub images of size 8x8. They are non-overlapping. That means no pixel is repeated. So I have a pixel here 512, say suppose. So if I am considering 8x8, I will have, say suppose this is one sub image. This is one sub image. My second sub image will start from here. Okay, so based on that, they are non-overlapping and they are of 8x8, right, in JPEG. Then we will do a level shifting. How are we doing the level shifting is, each intensity value is separated by the intensity value 2 power k minus 1. Okay, 2 power k minus 1. What is this k is? 2 power k is the maximum number of intensity levels in that image, right? So 2 power k minus 1, such that value is subtracted from each of my intensity value in that sub image, right? So using those values, we are performing the DCT transform and we get the DCT coefficient. So these DCT coefficients for the level shifted intensity values are calculated. Then using these DCT coefficient, we are performing the quantization. How is this performed? It is dependent upon this equation. So what is that equation is? So the coefficient, the quantization is based on this equation, which is given by t cap of u comma v is equal to round of t of u comma v by z u comma v. So what are these means? T of u comma v is the DCT coefficients. So t of u comma v is the DCT coefficient and z u comma v is fixed. It is fixed and it is called we got it from psychovisually tuned tables. we have read about the psychovisually tuned tables, right? So what is that table is, it is an 8x8 image. So this is called as a JPEG quantized matrix. It is an 8x8 because our sub image size is of 8x8. So we have a 8x8 quantized matrix where each value is specified. So these values are called as z of u comma v. So if we get a coefficient value that, say suppose we are having a coefficient value 3 comma 2 to be some minus 44. Say suppose this is our DCT coefficient value. Say suppose then we have to get our value z of 3 comma 2. So that is third row, second column. So this is 0 1 2 0 1 2 3. So this is my Z3, right? 2, 0, 1, 2, 0, 1, 2, 3. So Z of 3 comma 2 value is 29, right? So this T cap of U comma V is achieved by dividing minus 44 by 29, and this value will be rounded off to the nearest integer value. This is the how a quantization is performed in JPEG. So this, after we get this, whether we will get some minus 22, 0, 1 like that. So all these are ordered as a 1D sequence using a zigzag pattern. So what is a zigzag pattern is, I'll show it here. So it starts from here, we go here, then here, then here, then. So such pattern is called as so this goes like this. We go here, then we will consider this set of coefficients, then here, then this way. So if you observe that it is a very zigzag pattern, right? So this is the zigzag pattern that we are going to consider. So this is how the coefficients are ordered as a 1D sequence. So this 1D sequence are first used compressed using the run length. If we have a sequence of zeros and 1, then we are going to write it as run length. How is it? By we write the run length. Say suppose we have minus 5, minus 1, 0, 0, 0, 0, 1, 5, 3, 4. Say suppose our zigzag pattern gives a 1D sequence of this. So then this we can convert it as 4 zeros. Okay. So using this run length vector, we can encode it as run length, and then we are going using the Huffman coding and the compression model is achieved. So the JPEG is basically a form of my block transform where my subimage size is of 8x8 and the transformation technique that we are using is the DCT, right? So after that we are converting into a quantization model. So what is it quantization that we are method that we are using here is this by equation this. So T cap of u comma v is the round of DCT coefficients by the quantization matrix, JPEG quantization matrix. This is fixed for all applications. This matrix is fixed for all applications. This is standard matrix. So using these values, we will try to calculate my T cap. So after getting my T cap, I am using these. By using a zigzag pattern, I'm getting a 1D sequence, and that 1D sequence I'm passing it through the run length coding or Huffman coding to achieve the compression or compressed image, right? So this is regarding JPEG. In JPEG 2000, we are going to use the transformation technique to be, instead of DCT, we are using a wavelet transform, whereas the subsize and the other techniques like the quantization, everything, the masking, everything are very similar to your JPEG. Only the quantize or the transformation technique, instead of using DCT, we are using our wavelet transform, right? So this is about block transform as well as the JPEG and JPEG 2000. So this further information can be obtained from this reference book, which is the Digital Image Processing by Gonzalez. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.